We've seen how we can detect lane markings and how we can aggregate that lane marking information into lane estimates. But in the previous unit, what we did is we estimated the lane based on the observations from a single frame. And the problem with this is, of course, it's not very robust because we ignore all the measurements from the previous frames that might potentially be valuable for the current estimate. And also we've seen that we can't estimate the longitudinal position along the lane. And this brings us to lane tracking. In lane tracking, we want to formulate the estimation problem not for a single frame, but for multiple frames. We want to estimate in some way optimally with respect to observations from multiple frames with the hope of getting a better estimate. Exploiting information from the past, exploiting also maybe a model of how the vehicle moves, and measurements like visual odometry that tell us something about how the vehicle has moved. So all of this can be now integrated if they consider the lane estimation problem not for a single time instance but over a set of frames. Again, we're going to consider the model for straight lanes. And this localization problem is called incremental localization because we're trying to incrementally estimate the parameters of the lane over time. This is illustrated here on the left. We can see again in green, as before, the road coordinate system. And now we have the vehicle coordinate system at time t in blue and at time t+1 in purple. The rigid body motion that translates the a point from the vehicle coordinate system in time t to a point in vehicle coordinate system at time t+1 is given by the translation vector m and the relative change in the heading phi. You can see here in gray this is a copy of this coordinate system to better see how the heading has changed, and this is the change in heading phi. Remember that the heading we called psi, and now the change in heading we call phi. So these are three parameters, 2 for the translation and 1 for the change in heading in order to transform the vehicle coordinate system at time t into the vehicle coordinate system at time t+1. Or a point in that vehicle coordinate system into that vehicle coordinate system. We are going to use again the same state vector as in the previous unit. We want to estimate the lane width and the longitudinal and the lateral position of the vehicle, but now over time, as well as the heading of the vehicle over time. The first thing that we can do is define the so-called state transition equations. And they tell us how the state transitions over time. So here's what this looks like. If we go from time t to time t+1, then we have to start at time. This is basically in road coordinates, right? So we start with the parameters the position of the vehicle at time t, and then we add to that the translation vector that's now transformed by the rotation matrix that corresponds to the heading of the vehicle at time t. Right? This coordinate system here is not necessarily aligned with the road coordinate system, so we have to consider that translation vector here. We have to transform that first into the road coordinate system so that it is a translation vector in road coordinate system, and then we can add it. And so we obtain the position of the vehicle in time t at time t+1. Again, if we make the assumption that the heading angles are small, we can replace the cosine with a 1, and we can replace the sine with its argument. And so we get a simplified expression here. And we do this, as you will see, with the purpose of having a linear equation in the end. But of course, if you can use a nonlinear estimator, you don't need to make that approximation. And again, that approximation only holds, of course, if we have small heading angle in practice. Like if we're driving on the highway, in most cases, the heading angle will be very small. So this is the transition for the position of the vehicle from time t to time t plus 1. And similarly, we can write down mathematically the change in heading, which is simply taking the heading at the previous time step and adding the relative change in heading phi. And so we obtain the new heading psi t plus 1. And for the width of the lane, we assume that it's not going to change over time, so it's constant. So we have bt plus 1 equals bt. This is the state transition equation that tells us how we move from state at time t to state at time t plus 1. And in this particular case, because we have made this assumption here, we can write this down as a very simple linear form, which is given here, where we have the state at time t plus 1 equals a matrix times the state at time t times another vector. This matrix is the state transition matrix, and this vector is the input vector. And if I multiply those quantities and add them, then I obtain exactly these equations here. So we can see that the state transition equation is a linear equation. And so we can use very simple linear state estimators for this problem. Now, the other thing we have to consider are the observations, of course, right? Similar to before, we assume that we have NL points observed on the left lane marking in the vehicle coordinate system. Now, this is already transformed into the bird's eye view. And they are called XYL, YIL. And we have NR points on the right marking observed, which are called XY, XJ, R, and YJR. Now, YL and YR are given to us, but they can also be determined from the state and X, as we've seen in the previous unit. These equations that you see here are simply the equations that we've seen in the previous unit, this equation here, where we've seen that given X and the state, we can also estimate Y. So we have an estimate of Y, and we have the observations of Y, and we try to minimize the difference between these two, but not for a single frame now, but for multiple frames, or by tracking over multiple frames. Okay, so how does this look? Like here, you can recognize the equation again from before. So we have B half, for example, here, and then we have minus d lat and minus psi x1l. And in the upper part of this matrix, we have plus b half because we're looking at the left lane markings. And then at the bottom, we have minus 1/2 because we are looking, minus b half because we are looking at the right lane markings. And we can also see here that the observation matrix, or the observation system, the observation equation, is a linear equation. The predictions for Y are given by a product of a matrix with the state vector. We can make predictions about Y based on a matrix multiplied with the state vector. And this is also illustrated here. So for example, for a particular X location, we have the observations XY, so we take one observation X now. The model, given the parameters of the model, can make a prediction for where on this Y-axis of that vehicle coordinate system this lane marking would be located. And this is simply the intersection of this line that we see here in purple with the lane markings in red. And that's described mathematically here. Okay. So now we have both. We have a linear state transition model and a linear observation model. So the entire state space representation that combines both the state transition and the observation can be simply described as two linear equations. The state at time t+1 equals a times the state at time t plus the input vector. And then given the state at time t+1, we get the observation at time t+1 by again multiplying that state with a different matrix C. So we have, for this estimation problem, we have a linear dynamic model, we have a linear measurement model, and if we now assume Gaussian noise, we can estimate this optimally and in closed form using one of the most famous state estimation algorithms that you probably have heard about before, which is called the Kalman filter. I'm not going to go into the details of the Kalman filter in this lecture, but I'm just going to tell you that the Kalman filter can solve such simple Gaussian linear systems, Gaussian linear state space representations effectively and optimally. But the reason why we can do that is, of course, that they are linear and we assume Gaussian noise. So this works only for very simple models. And now you can see why we made all these simplifying assumptions such that we can actually apply the simple state estimation algorithm. So how does this work in practice? Well, in the first stage of this algorithm, we need to detect the road markings in the image, of course, and then we need to apply the inverse perspective mapping to transform the detected road markings into the vehicle coordinate system, the bird's eye view that we always visualize here. Then we have a prediction step, so we can, for example, determine how the vehicle is moving. Say using a visual odometry, we can transition the vehicle forward. And this gives us information now about the lateral position with respect to the lane. But this will not be optimal. So you can see here that we have transitioned from blue to purple. But the observations that would correspond to this purple coordinate system are offset to the actual lane markings, while we observe the lane markings here in red. That's why in this Kalman filter we have the innovation step that then integrates the prediction from our motion model with the actual measurements and corrects the state based on both the prediction and the measurements through these Kalman filter update equations, right? So we do a prediction and then we correct with the current measurement. So we update the state with respect to the observed markings, and that's shown here in brown. So now we have changed the prediction. The prediction doesn't make any use of observations yet. We just forward propagate with a noisy visual odometry measurement, and so that's not perfect. We have error accumulation and so on. But now we observe the lane markings, and so we can correct for this offset. We don't know much about the lateral position, right? But we can, the longitudinal position, but we can correct the lateral position and the heading because we have a lot of information about these. And so after correction, you can see that the coordinate system at time t+1, right? So this is both the purple one and the brown one are at time t+1. The first one is the prediction. The second one is the final correction with the observations. Now this final correction at time t+1 is better aligned with the lane markings because it utilizes the observations, it utilizes the observation model for this correction step. Okay? This is how a Kalman filter can be used to track the lane parameters over time through observations of the lane markings. Of course, straight roads are not sufficient to model all driving scenarios. So another model that we might want to consider is a circular lane. If you have a circle and you let the radius go towards infinity, then you even obtain, as a special case, the straight road, right? So we can, by specifying the radius or the curvature, which is 1 over the radius, we can transition between a very sharp turn and a straight road. So it's a more flexible model than the straight lane model. What does this geometric model look like? Well, we have the lane width again, but now we also have the signed radius, or the curvature, which is 1 over the radius, as a parameter, as a state, as an element in our state vector. We have the lateral vehicle offset, in this case with respect to some, like the path that's defined by the radius, the circle path. And we have the longitudinal position along the circular trajectory. And then we have, of course, also the yaw angle with respect to that trajectory. And so the state vector is augmented by one variable here now. And this model cannot be represented using linear equations anymore. So it becomes nonlinear and therefore requires more sophisticated state filtering techniques, such as the extended Kalman filter, or the unscented Kalman filter, or the particle filter. Maybe you've heard about these also. Now, even circular trajectories are not enough. For example, if we move from a straight road segment to a circular segment, which seems plausible at first glance, what happens is that the curvature increases with a step function. The straight line has a curvature of 0, or a radius of infinity. And then as we transition from here to there, this curvature jumps to the actual curvature of the circle. And what that means is that also the acceleration jumps. You will see this in the exercise. This is also the reason why, for example, roller coasters are not built like this. They are not built with straight line and circular segments, because it would lead to a very large so-called jerk, which is the time derivative of the acceleration. So it would be a very unpleasant and actually unhealthy ride experience if you do that, because at this point you observe a sudden jerk on your body. And so what's better is to, of course, slowly transition from the curvature of the straight line, of the straight lane, to that circular trajectory here, so that we go from 0 and linearly transition to that circular curvature, because then we don't have this jump in acceleration, or this infinite jerk that is induced on the body. And that's why in practice, when road designers design roads, they always use the so-called Clothoid model. That is exactly this model that can transition between a straight line segment and a circular road segment. And for example, this is needed when exiting a highway, for example, and you're going from a straight line, but you have to turn into at a relatively high speed. So the higher the speed, the more relevant it is to minimize jerk. So you're transitioning slowly to the target curvature. And this is illustrated here, where you can see that the curvature slowly increases until we have reached the curvature of the circle, compared to directly jumping towards the circle curvature. And that's called a clothoid. Mathematically, what is a clothoid? Here is the pure form of a clothoid drawn as a trajectory. A clothoid is a curve whose curvature linearly depends on the arc length. This means 1 over the radius, where the radius is defined with respect to the arc length. This is the position along that path, or here along that path here, which is the curvature of the arc length. It's just a linear expression with respect to the arc length, the position along that path. This is the expression that defines a clothoid. What does this mean? Well, This means that, for example, the yaw angle, which is the integral of the curvature from 0 to L, becomes a quadratic equation, because now we are integrating this expression. It becomes a quadratic equation with respect to the path length or the arc length. And now if we want to obtain the position, we have to integrate again. We have to integrate this expression here again. For x, we have to integrate the cosine of the yaw angle. For y, we have to integrate the sine of the yaw angle. Now, if we assume small angles again, then the cosine can be approximated by 1 and the sine by its argument, where the heading, the yaw angle, is given by this quadratic expression here. And that means that we obtain a third order polynomial. For the x coordinate, because we have assumed small angles, we assume highway driving, let's say, we simply get L. But for the y coordinate, we obtain a third order polynomial expression because we have to integrate that quadratic here. So it's clearly a nonlinear expression, but we can still solve the tracking problem by using nonlinear state estimators, such as the extended Kalman filter, for example. And this has been done in this seminal paper by self-drying pioneer Ernst Dickmanns from the Bundeswehr Uni in Munich. We have seen already some of his results in the history part of this lecture. So we're not going to go much into detail. It's very technical and mathematical, but I'd like to highlight this paper here. It's called Recursive 3D Road and Relative Ego State Recognition, one of the seminal papers for state estimation for self-driving vehicles. It uses a visual recursive state estimation and a Clothoid model, but applied not in the simple 2D case, but actually in 3D. So it models the horizontal and the vertical road curvature, as we can see here, through clothoids. It considers a dynamic bicycle motion model, and it uses a projection-based measurement model instead of inverse perspective mapping. So it doesn't assume that the measurements are inverse perspectively mapped into the bird's eye view, because we are also modeling the vertical road curvature. So we have to integrate this measurement model also, this more complex measurement model also. We have to consider all of these curvatures when projecting points from 3D to 2D. But that can be now integrated because we don't want to restrict ourselves to a linear state estimator. So if we can use any nonlinear equations, then we can of course also integrate the pinhole projection into this process. In summary, today we've seen that road and lane detection are important topics for advanced driver assistance systems and self-driving in general. We've seen that they allow to localize locally with respect to the road without requiring a global map. There's multiple different representations with their individual advantages and disadvantages. We discussed road segmentation and lane marking detection in the beginning. And we've also seen how lanes can be estimated from lane markings, how lane marking information can be integrated into whole lane estimates. We discussed how we can incrementally track lanes over time, but we haven't addressed the geometric free space estimation part that was also discussed or introduced early in this lecture in the overview. And we haven't discussed that yet because we haven't discussed 3D reconstruction, and this will be the topic of the next lecture. And so we'll also have a little unit that discusses free space estimation in the context of 3D reconstruction. Thanks.